So we are going into our discussion, no, on waves. No? And why is it important for us to learn about waves? No? Nga akin ang naton matun-an ang waves. No? Again, waves is not just the one nga makita naton sa dagat, no? Nga nagadapya ang balod. No? But the significance of waves in physics is that ang mga energy nga gina-produce naton from one place, no, or from point A no nga lugar, say dira kita naga-create sang energy, no, like electrical energy, no. Now kinahanglan siya naton nga dalon sa layo nga lugar, no, sa point B, no. Maybe that's a few meters away or maybe that's a few thousand kilometers away, no. So depende kung ano na siya kalayo, no. But there's a need for us to let that energy travel over a certain distance. No? Nakaroon, kung wala kita sang means of making it move, no, from A to B, no, whether the distance is short or a very long distance, then no, again, no, it will be useless to produce that energy in one place. No? Okay, nga mag-generate kita sa amo ng energy. No? So therefore, now what comes in will be the importance of these waves. No? Waves are carriers of energy. No? Why did we consider waves to be carriers of energy? Is that, for example, no, I created this ripple. No? So I believe no, you are seeing this image here on the screen. No? This circular thing, no, that when you drop, no, kung may ihulog ka di sa tunga sang tinaw gid nga tubig, no, maybe bato or anything, no, maka-create kita sining do bilog nga nagabalod, no? Kagang ini nga daw balod, naga-move outward, no? Halin di sa tunga, no? Makita natin siya nga nagapagwa, na. Amo ni outward motion na no? Now, we call this, no? Kung isa lang ni siya kabilog circle, we call it as a ripple, no? Hulugan, da nimo or itos mo mo tudlo, you can create this, no? Now, why did I say nga gina-carry or ginadalaya ni ang energy, no, halin di sa tunga? It's because, no, for example, ibalik naton ang kondisyon nga tinaw ni siya, no. Maobra ako sang gamay nga paper boat, no. I will fold a piece of paper and eventually create a paper boat, no. Now, for example, I am done with a paper boat. Ipalutaw ko diyang paper boat sa layo nga part, no. Somewhere here, no. So, let's say kung labador na, dito sa may kilid gawas ang labador, no, kag ipalutaw ko dito ang paper boat, no. Now once I let the paper boat float, no, and I'm going to disturb this part, no, ito smaw ko akong tudlo di sa tunga, manotice ko ngang disturbance as it moves away, no, dugay-dugay makalabot na siya sa papel di nga paper boat, no, and dugay-dugay ang paper boat masaka panaog na sa, no. Now the point is, wala ko na gintandog ang paper boat da, no? Pero nga nagahulag na siya subong, no? Because again, no, the energy I created here in the middle was brought, no, by the waves pakadto sa paper boat sa kilid, no? So that's the idea, no? Ng energy nga gina-create gali naton, we can let it travel, no, over some distances, no, by virtue of waves, no? So again, no, you'll see that the boat now will bob up and down, no? Sa kapanawag na siya, maskin wala na siya gintandog, no? Again, no, the essence of carriers of energy, no, which we call as waves, no? Now again, a wave is a kind of a disturbance, no? Most books will call it as a disturbance, no? And ang iya pag-propagate or ang iya nga paghulag, no, is always, no, from the region where you disturb it, no, then pa gwa, no, or palayo sa sinang location, no. So wave propagation is important, no, in transmitting energy, no. Now may ara kita nga waves, guys, nga ginatawag naton mechanical, no. Kung natawon naton duwa na siya ka grupo guro, no, mechanical kag electromagnetic waves, no. Now, ano ni ang mechanical waves, no? Any mechanical waves, no, can be classified, no, as a kind of a wave nga nagagamit siya sang medium, no? The word there that distinctly, no, identifies mechanical waves is that it uses a medium, for example, air, water, no, maybe a string, no, cable, or ang earth, no? Kinahanglan siya nga may amo na, no? Para nga makaulag ang wave, no? Kung absent ang air or water, no? Wala sang wave nga makita, no? Or wala sang string, wala sang wave nga makita, no? Amo na ang classification sang isa ka grupo sang waves, no? Mga mechanical waves sina, no? And these waves are present in our sound, no? Sound wave, no? Kung maghambal kita, nagagamit na siya sang hangin, no? For us to hear people, no, talking, or if you want to listen to somebody, kinahanglan may hangin sa tunga. Kung wala nang hangin, hindi natin sila mabatian, no? Water waves, no, kinahanglan sang tubig na, no? Ang earthquake, no, kinahanglan mo na siya sang duta, no? The ground is important, no, para nga ang wave will be able to travel, no, if there's an earthquake, no? And lastly, no, ang string, no? If you have a guitar, if you have a kind of ano ni nang may higot kada no pag imo nga ipatikon no i-move mo, you'll notice that there is now a traveling wave in the string or in the cable, no? So kinahanglan siya nga may higot or may string yan, no? Without it, you won't see anything there moving, no? Now, ining mechanical waves will need these things which we call as a mechanical medium, no? Ano ni mechanical medium again? Water, air, solid earth, no, or stretch spring, no? So they are needed in this kind of wave, no? Now, ang wave nga wala nagagamit sang medium, no? Hindi siya wala siya need sang hangin or tubig, no, para nga maghulag siya. Amo ni ang EM or electromagnetic waves, no? Okay, so wala sila sang mechanical medium, no? They do not need water, air, no? Pero naga-travel sila gyapon, no? Despite the absence of this medium, no? Now, example sina ang mga light waves that comes from the sun, no? Now, ang distance halin sa sun pakadto sa earth is an enormously, no, long distance, no? It may not be really, no, that hindi gina siya mo ng pinakalayo nga distance in the universe, no, because there are a lot more. But 93 million miles is also a considerable distance, no? And in between the sun and the earth, there's nothing there, no? Wala hangin, wala na da tubig, wala na da duta, no? But still, no, the light from the sun, if it is a wave, no, and it is considered as a wave ang light, nga nakalabot siya sa earth without this air, water, or ground, no? Because it does not need it, no? It's called as an electromagnetic wave, no? Now, ang radio waves, no, ara lang na siya di, no? Amo ning mga unod sa aton electromagnetic waves, no? Iban nga portion sa aton nga wave nga ini, no, laba-laba ning electromagnetic wave. May ara na da nga part, no, nga light siya, no? Nga makakita kada nga may white light, no? But it's only a small segment, no, of that long spectrum of electromagnetic wave, no? Now, diri sa may punta or sa mga short wavelengths din, no, ara na di ang mga high energy, no, high energy waves, no, mga gamma, x-ray, no? No, medyo delikado na nagawa. And then diri naman sa may long wavelengths, no, ining do layuan ay gawang mga curve, no, are your radio waves, no? Ginausab naman na sa communication, no? And other things, no? So again, no, ang aton nga electromagnetic waves, now hindi ta pa siya matakol di subong because this is part of our, no, physics 2, no? So we will introduce it back, no, in our physics 2. No? So EM waves, no? So versus your mechanical waves, this one, no, does not need a mechanical medium, no? Now, you will considerably notice no, nga may flash din ng microwave, no? Now, this microwave is useful, no, also in communication. Sa aton nga ano ni, cell phone, I think, no? They use also microwave signals there, no, to be able to transmit, no, our communication, no? So it's not only present ang microwave, no, sa aton nga kitchen for our microwave oven, no, but it's also even useful in communicating, no? Now, waves, no? These are periodic repeating disturbance, no? So kung may hangin gani nga tudo, makita na naton ni aton nga dagat no nga nagabalod na sana. So may nagadisturbo abing hangin sa dagat. That's why this is now created. No? So sometimes these are very high, no? And usually, no, the waves, the height of the wave is dependent, no, kung may duta na siya nga malabot, no. So for example, no, may part ng sang duta nga didto pa sa dalom nga part sang dagat bala. As it, no, reaches that part, pwede kay masaka na ang wave na ton as dagi nga maglabot sa shoreline, no. The height of the wave probably will be highest, no, kung lapit na siya gawa sa duta, no. And again, no, that's the nature of the height of the wave, no. We will not see the height of the wave usually, no, kung wala duta pa, no. So manotice na to na pabalik-balik na sana. So may hara na siyang timing, no. So if you are there, no, in the middle of the ocean and then the wave passes by, no, you'll notice that you will move up and down, no, on a regular interval of time, no. So kung timean mo na, no, you'll notice that you will probably move, no, in every number of seconds, no. Kag may pattern siya, no, paliwat-liwat, no. So that's what we mean by periodic, no, paliwat-liwat. Okay, our waves, guys, no, when we disturb it, no, would probably be thought of as something like this, no. So you start the disturbance in the middle, and then it is moving outward, no. Now, our question is always, why is it always shaped circular, no? Bilogid, no? Again, no, the nature of the particles of our wave is that they are, no, side by side, no, ang mga particles sa aton nga tubig, no, ara gina sa tupad ya. And when you disturb a portion of the water, no, the water particles around it is also disturbed at the same time, no? Dungan sila disturbo, no. So therefore, when you disturb one of them, no, and they disturb the nearby, no, particles, synchronous na sila, dungan na sila nga ma-disturb, and therefore they will move outward together, no. That is why as they move outward, no, they will be shaped, no, in a circular manner, no. But our question, are all waves always circular, no? Maybe not, no. If I'm going to dip a straight edge, no, a ruler in water, no, manotice mo kung itusmaw ko ang ruler sa tubig kag hakwaton, hindi man na circular ang ma-create ko, no. What I will create as a wave there will be a parallel, no, wave fronts, no. Tadlong naman yung mga waves karon ako makita sina, no, kung i-disturbohon ko ang tubig using a straight edge. Pero kung i-drop ko lang ang tubig, no, mahulog ko sa isa ka bagay kag i-disturb ko ang isa lang gid ka gamay nga portion or itusma ko tudlo ko, circular na ang ma-create yan, no? But again, no, we can also create other shapes, no, like a straight line, no? If you dip, no, a straight edge also in the water, no. Now I think we will go back to why, no, it is circular later, no. Okay, now usually, no, ang aton nga pag-enchant ang aton wave, no, is that ang particles wala na yan nagahalin sa ila lugar, no. They do not actually, no, travel, no, the particles, no? So when I say particles, no, so if you are to draw a line, no, on this red particle here, no, you'll notice that the wave appears to be moving, no. It seems that the wave appears to be moving, no, from left to right, no. Kung ang tawag nato ng wave na ito, doon nag-travel pa mo ni, no. It would seem to be moving in that way, no, as you let the disturbance, no, go on, no. So if we will try to notice, no, it would seem that the wave is moving from left to right, no. So the way it behaves, no. So doon nagahulag na siya from left to right, no. But in reality, no, just check this red particle, no. Ining red particle is one of the particles of the string, maybe, no, or of the medium. And you'll notice that this red particle is simply moving up and down, no, in its place, no. Actually, it is not traveling from left to right, no, inang red. Ara lang na sa, no. And it is simply moving, no, in that same location, but it is moving up and down, no. So the particles are moving, but there's also a wave direction that is occurring, no. Ini nga tong wave direction amo na ni karon ang naga-appear nga nagahulag seemingly no from left to right no. But in reality no ang kada particles ang wave wala na sila nagahalinda no. Nagasaka na og lang sila no. So this is how the medium probably no is working no. Now this kind of wave guys no we term it no as this is classified as a transverse wave no. Ano ning ginatawag natin nga transverse wave no. So again now in every material no string kung may string ka sa guitar no that's a medium no. Amo to kay na nakita natin nga nagdo snake like no. The particles of that string simply bobs up and down no. Now that one is also described as a transverse wave no. The particles there simply move up down no, but the wave seems to travel no from left to right no. So amo na no we describe the first type of wave as transverse wave because the particles no move perpendicular to the wave direction. The wave direction is moving left to right, but the particles move up and down. No? Therefore, they are perpendicular to one another. No? So ang particle nga A niyo nagasaka na og lang na siya. No? Pero ang aton wave nagahulag siya no left to right. So kung nantawon naton do 90 degrees na sila or they are perpendicular to one another. No? So we call that no as transverse type of a wave, no, and that's how the disturbance no is being propagated. No? Now, so this is another way of looking at transverse waves. No, so each particle is just going up down. Now you notice that this particle here, no. May ara ni siya kadungan nga particle no dungan sa maghulag no. Let's say no you'll notice this one no the very first particle here may ara ni siya nga kadungan nga wave nga particle no nga dungan sa ila hulag no. Now for particles that move in the same direction at the same time no we call them as in phase points no or in phase particles no. Natabala kung sino ning kadungan niya sa una-una niya no. Now, somewhere here, now in this series of particles that moves up and down, mayroon na siya nga kadungan. No? So, madungan na sila saka, dungan sila panaog. No? And again, we term that particles that move together as in phase. No? In phase points or in phase particles. No? Now, in phase particles determine what we call as wavelength. No? And usually, a wavelength, no? is symbolized by no this somehow no an inverted symbol nga the y no. So usually they write wavelength as something like this no. They term it as lambda no. That's the Greek letter called lambda no ang gina-denote sang wavelength no? And usually no wavelength is measured in, no? So the unit of wavelength, no? Our wavelength is measured in meters, no? Because that's a unit of length. No? Now, how do you know again a wavelength? So a wavelength is determined when you have two in phase points. No? So this lowest portion of this transverse wave, no? Maybe no they move together no so this one moves up down no in the same timing no as this side no so they are considered as one no in phase two in phase points no. The lowest points here are considered trough and the highest points here are considered crest no. So between two crest or two trough you can get your wavelength also no. But you'll also observe now that there are portions here of the wave guys no that do not actually no nga wala nagahalin sa ilang lugar no may mga part na sa wave nga wala nagahalin sa ilang lugar no. And maybe now that happens when you have what we call a harmonic, no? So kung may ara kanang harmonic na ma-produce, no? Or a standing wave, no? So again, talking about waves that are having in-phase points. So in-phase points determine a it determines a wavelength. Okay, so these are what we call now another kind of wave, guys, is the longitudinal wave, and this is a little bit more different than our transverse waves, So in what way they are different, or they are not the same as our transverse waves, So this is the second group, of waves that are under mechanical waves, So this one also needs a medium, But why do we consider them as longitudinal wave, Now, think about air, And air, has some air columns, So these particles B, C, D, E, F, G, H, I, are, let's say, for example, they are considered as air columns. There are a lot of them. Now, what do we notice about these air columns? At the very beginning, they are equally spaced. They are equally as far as each other. So, ang A to B is the same distance as B to C. And for example, this is the air columns during a time when you did not disturb the air first. Wala mo pag-indisturbo ang hangin. Now, when can you disturb the air? Maybe when you start talking. If you start to talk, then you'll disturb the air columns in A. So supposing your mouth is somewhere here. Now, what will happen to A as you disturb it? Then most likely it will go near, or it will move forward, kay gindisturbo mo siya, So madasok na sa B, C, D, E, or ining mga particles will now get closer to one another, But again, you'll realize that this is not their usual state, kung nagadinasok sila, So what is their tendency? So D, since it now has this nearby particles na C and B and A, So ang D karon, its tendency is to keep that distance, nga layuanay sila. So ang matabo, ang D will now move towards E, F. Papalapit na siya sa direct na side, However, as D is now trying to move towards the nearby columns sa tuo, ang ato naman nga A, B, and C, since hindi na sila anad nga lapitanay sila, they will now return to their place, Their tendency is to go back to their place. As D is trying to move to the right, A and B and C are trying to return back to their regular places sa ila equilibrium state. So as they go back to their equilibrium state, mabalik sila sa ilang usual nga lokasyon or places. Then ang matabo, may mga parts karon nga naglayuanay na. Now we term these particles that are now moving away from one another as a rarefaction. So rarefaction happens, and then again, you'll now see that the waves here na naghulag na karon, nagaabanti na siya, So now the disturbance is in D, E, F, G, H, I, and therefore we see an advancing wave that is also going from left to right, until the person on this end hears you, if the disturbance is a sound wave. Now again, this one will not happen in stages, nga amat-amat. But when we talk, we see that we will notice that we are immediately heard, So this one will happen in a snap, Dasig-dasig ni siya matabo, So as an illustration, however, we see it in stages, but this is not occurring, nga hinay-hinay. Now, one thing we realize with the movement of the particles, A, B, C, D, E, that they are moving back and forth, left, right movement, That's the movement of the particles, And at the same time, the wave direction is going from left to right, Now, we will see here that the two motions are now parallel to one another. No? So therefore, we describe our longitudinal motion, no, or longitudinal wave as having, no, these two motions to be parallel to one another. No? The particles move parallel, no, to the wave direction or motion. Okay, so again, now this is happening in sound waves. No? So how fast are waves actually traveling? I think now they have an estimate of around 340 meters per second. No? That's how fast it is moving. No? So again, the significance of our our longitudinal motion, longitudinal wave. No? So there's a series of compression and rarefaction that is occurring, and then therefore, wave is not able to be propagated. Now, this is how you probably talk. So that's how fast it is moving. And we see that in our series of compression, and sometimes they call instead of rarefactions as expansions. So when particles are further from one another, because they are being stretched or being compressed in some other places. So may mga parts na nagalayuan na sila. So between two compressions or maybe between two expansions, you can also consider a wavelength. So that could be considered as one wavelength. Now, the similarity of transverse and maybe longitudinal wave. And this is actually happening to the water waves ara sa dagat. So they call the water waves as a surface waves, and it is both transverse and longitudinal. Kaya ang tubig is a compressible material that longitudinal waves are able to travel to. Okay, sound waves can travel through air and maybe through metals, through solids, and maybe through water. Pwede na siya natin mabatian sa liquid. Now, the general word for liquids and gases, we call them as fluids, because we coin the word fluid as for things nga naga-flow. Ang solid, ya kung iula mo, hindi nasa pareha sa liquid or gas. Gas has an ability to flow. So why do we consider that has an ability to flow? You can use a gas as a brake. Gamitin mo siya for braking systems ang salakyan. Pwede na ang hangin because the air can be delivered from one part of the engine to the tires. Pwede mo siyang i-pressurize kag i-flow from one location to the other. But solids do not probably do like that. So hindi mo siya pwedeng i-push. Okay, surface waves, again, for water waves, we could think of it as something as a rolling kind of wave. Ara ko na sa aton nga surface waves. So it's circular in nature, but it seems to be moving up and down as well. Because again, it is having this rotating type of motion. Now here are our properties of our wave. The highest part of the wave is known as its amplitude. Either we move up or we move down. The highest point there is known as its amplitude. The distance between two in-phase points are known as wavelength. The time for one wavelength to be created is known as a period. So period is a time, is a symbol or notation for time. Commonly we write amplitude with capital letter A. I indicate that with capital letter. Lambda, seemingly this inverted letter Y of the Greek letter is symbolized for wavelength, which is measured in meters. And period, usually we symbolize it with letter T, capital letter T. Frequency with small letter F. And wave speed, or wave, speed of the wave is symbolized with letter V. And I think F, T, and V, and including lambda. So lambda is symbolized with an inverted Y, something like an inverted Y. they can be related to no in a kind of an equation. No? Again, no, for sound, sound travels roughly no in room temperature around 340 meters per second. No? If you heat up the environment no, or the surroundings of air, air will travel much faster. No? So the speed of sound, no, or I mean, no, the speed of sound, I mean, no, will travel faster no, in hotter air, no, if the air is much more hotter. No? So temperature has an effect on the speed of the wave. No? It means no, for warmer or colder environments, speed of sound will move no a little bit more slower. No? Here are these properties no illustrated in this diagram. So the amplitude could either be going up no? Or maybe it can also be considered going down. No? Usually the lowest points are called the trough. No? Others pronounce this as trough. Others would pronounce it as trough. No? I think I heard some no? pronouncing as trough. So lowest points now, so the two lowest points can be considered as a wavelength, or the two highest points can be considered as a wavelength. No? Now, a single wave, no, maybe you can measure now one wave not to be from this starting point until here. No? This is one wave, no? And that is one wavelength also no? From this point to the other point. No? So you can have lambda there. No? Now you'll notice that the wave repeats no, for this next interval. No? So after here, now you'll notice that it will again repeat no, up to this point. No? And again, it repeats until this particular point. No? So we will notice that for this particular number of waves, no, there are three vibrations. No? So there are three vibrations actually, or three cycles no, that we see. No? And if this is produced in a second, no, then we can probably no, know its frequency. No? So for example, that occurs in 1 second, no? These three vibrations in 1 second. So its frequency will be three vibrations no? Per no? second. No? Okay, so others usually no, write VPS. No? If it is cycles per second, no? Others can also write that as 3 cycles per second. Or CPS, no? For others, we'll just write no a shorter way of writing it, no, as 3 hertz, no. So hertz is also a symbol of the unit of frequency, no? Hertz, no, or Hz. No? So a symbol for hertz, no. So this one again, if you see this, there are 3 vibrations here. Now, each of these portions that I mark now are considered in phase points, no? And they are no? Along the equilibrium line no? Or equilibrium point. No? So we have amplitude, we have wavelength, no? We have frequency. And again, if we are able to know no? The time no, for this wave to be created. So for example, from here no, up to there is 1 second. So maybe no, one wave can be created no, with merely no, a period of, so the period of our wave, no, if we will try to find it, no, if the frequency is 3 hertz no, or 3 cycles per second, then the period will be 1/3 no, of a second. No? One wave is created 1/3 of a second. No? So I think no, that is simply dividing 1 by 3, no? 3 waves. No? So you will have there no, 1/3 of a second. No? If you have no question, then we move on no, to another part. No? So here are our waves. No? So we mentioned about the word in phase a while ago. No? Now, if you look at this diagram, no, there are particles here that are actually now moving up together, no? Like particles 4 and 12, no? They move in the same direction. No? So maybe you can consider points 4 or particles 4 and 12 as in phase. No? Particles 1 and particle 9, no? They are in the same place and they move in the same direction. No? So again, no? 1 and 9 are in phase points also. No? Now, there are also points here that are in the same place, the same location, no? The same line, but they move no, in two different directions. No? And for that, no? So like for example, no? Points 2 and 4. No? Maybe 2 and 4, they are in the same line, but they move no, opposite one another. So they are considered out of phase. No? Like 1 and 5, they are in the same line, no, but they move no, opposite one another. So they are in out of phase. No? So the opposite of in phase is out of phase. No? Again, on the significance of in phase, we are able to determine the wavelength there. No? We are able to know no, how to measure one cycle of a wave no, by knowing in phase points. So in phase points are 1 and 9, and that is how, no, or that's how long is one cycle of the wave. No? Knowing the one cycle, we are able to find the period, the time no, for that wave to be created, including the wavelength. No? So if we are to measure or count no, how many waves are formed, then we can also look at no, these in phase points. No? So for this example, probably no, we see something like 2 waves no, are created no, in this illustration. No? So in phase points. No? So these 2 successive in phase points are considered as one wavelength. Now here's a relationship between wave speed no, with wavelength and frequency. So multiplying frequency and wavelength, no, we get the wave speed. No? So maybe in a formula, no, we can write as V no, is equals to maybe now you have here your frequency F, no, small letter F, and we can pair that with our lambda symbol. So this is now our no, wave speed. No? V is lambda F. No? Or if we write no, in terms of our period, guys, no? Or in terms of, yeah, in terms of our period, we can also write no, V can be written as lambda F. No? So if you will divide no, 2 values, so we can divide no, our wavelength by our period T. No? So what's the relationship of the period and the frequency? They are inversely proportional to one another. So if you will look for T, T can be equated to 1, no? 1 over F. No? So again, no? 1 over F means that they are reciprocal no? to one another. No? So if you get the reciprocal of frequency, you'll get the period, or the reciprocal of the period is the value no, of the reciprocal of the frequency. No? So balis kada na ilan na sila nga dua. No? And again, here you can use it in this symbol. No? But out of this equation, if you look at the triangle on the right side, no, we can also express no, frequency in terms of wave speed no, over wavelength. No? Or wavelength lambda can be the ratio of speed over frequency. No? So again, this one that I boxed no, can be interpreted here no, in this triangle that we have on the right. No? Now, I think now you can try this no, on these different values that we have here, no, or examples. No? So you can use the triangle here no, in calculating for any of these values. No? Now, we will take time to answer that, no? Maybe no, next time. But moving along, no, we have additional exercises here. No? So we have 9 examples there. No? Now let's go into wave fronts. Now, what are these wave fronts? No? When a wave originates no, at a particular point, no, such as a point no, on the surface of the water, no, the wave will propagate no, in a horizontal plane no, from this point. No? The wave spreads out in circles and is a familiar sight now when a stone is dropped into water. Of course, that's what we mean earlier by this ripple. So this is what we see in our water surface. So again, the disturbance is always starting in the middle, or we can call that as a point source of disturbance. Then it moves circular outward. And if there's a boundary here, di por parte nga hindi na makantuan, mabunggo na siya kag magbalik. So that is if you put an obstacle or a barrier diri sa palibot. Pero kung wala lang, kung libre lang na siya kag dako-dako, then this shape will simply move outward until it dissipates. So wave fronts are this circular thing that we see. Amo ni ang bilog na makita naton. Amo ni ang ginatawag naton circular wave fronts. Kag naga-advance na siya. Naga-advance na siya pagwa. So may ginhalinan siya nga source S, or point source, kag ginadisturbo ang particle sa tupad in all directions. That's why we see a shape there nga bilog, a circular shape. Now, ang explanation nga bilog is explained by this Huygens principle, formulated by a Dutch physicist named Christian Huygens. So si Huygens nag-explain sini, nga bilog gid na, why is it always shaped circular, nga hindi na siya lain ang shape. Again, we've seen earlier nga atong illustration naton that the disturbance when they are created, they are advancing particles nga na-disturb nga nagadungan. They are moving simultaneously. So since dungan sila, they will be shaped circular. And they are moving in a direction nga bilog. Napabilog sila. So again, the one who tried to make an explanation of that is Christian Huygens. I don't know if I pronounce his family name correctly, but it's Dutch, and I don't know how to pronounce it. Others will pronounce it as Huygens, but it comes with whoever's reading that family name. Now, another concept in waves is interference. So when waves come together, let's say we have now wave 1, 2, 3, 4, 5. When they come together, then they will now interact with one another. As a result, maybe we could create, if there are two waves that will come in contact with one another, we can expect that this wave will now become louder if it's sound, or it will become higher, ang height, because they are aiding or helping one another. Now, if the wave becomes bigger or louder in sound, then that's a kind of an interference of waves, or interactions of two waves that is considered constructive. So wave 1, wave 2, they combine or nag-superimpose ang isa sa ikaduwa, kag nagdako ang wave. Okay? Ang result yan nagdako. So we call that as constructive. But not all interference is constructive. There are other kinds of interferences that are considered destructive. So destructive interference is when wave 1 and wave 2, supposing ang wave 2 yung baliskad ang niya shape, sang sa wave 1, assuming that these two types of waves comes together. Now, what will happen after they interact with one another is that they will cancel out the effect of each other. And what happens is, you will not hear anything anymore if it's sound. Madula na sa. Okay? I think there's an activity that they perform by doing that using two kinds of sound in two speakers. Kagin they did one, they did something to the other one where the waves are now opposite the other. And when they brought it together, when they brought them speakers together, the sound becomes naghinay. Maskin wala nila gina-adjust ang volume, naghinay kaya naga-cancel out sila galing nga duwa. Okay, so again, a way of canceling two waves. That is if you have two interfering waves that are destructive to one another. So there's a cancellation, and then the eventual result is that the wave is gone. Nag-equilibrium na sila nga duwa. Okay. So again, that's in comparison to our constructive interference. No? So these are the two types of interference, no? The constructive and the destructive one. Now, another type of behaviors of waves is when they bounce, no? So they bounce off, no? So if you have here a barrier, I consider it as a barrier, or that is now boundary, no? So may hangin sa babaw, may tubig sa dalam. So ang iniding part, boundary, no? Now, when waves encounter a boundary, no, there's a possibility nga pwede na siyang mag-umpok, no, mag-reflect, no? So if it's sound, then you will hear an echo, no? Kaya nag-bounce back ang sound, no? So reflection is an example of the bouncing back, no, of the wave, no? Now, one thing we notice about the behavior of reflection is that may ara na siya angle of incidence, no? Pag may angle of reflection na siya, no? Kung sa reflection sang wave ang atong istoryahan, ang ina nga duha ka angle are equal, no? So they are usually measured from this vertical line. This vertical line is called as the normal line. Yung natawag natin na normal line. Normal line because it's perpendicular to this boundary or surface, no? Now, ang ilang angle again, no, are both equal. Angle of incidence and angle of reflection. Ang angle of incidence is the angle formed by the ray, no? Ang tuod yun nga ray of light, no? They call it usually as the incident ray, no? Commonly, no, we refer to the waves, no, also as light rays, no? So, no? So once it bounces back, no, then they will form two equal angles, no? Now, ining tatlo kuno ka line, ining incident ray, ining reflected ray, ining normal line, they all belong to the same plane, no? Now, the things that I just mentioned, no, are part of the law of reflection, no? The angle of incidence is equal to the angle of reflection. No? That's number one law. That's the number one principle of law of reflection. And then the third one is these three lines, no? Incident ray, normal line, reflected ray, they belong to the same plane, no? That's principle number two, no, of the law of reflection, no? Now, for refraction naman, no, that's another principle, no? Refraction is the bending of the wave, no? And saan bend ang wave, no? Ang wave nag-bend siya kuno, like this one, no? There's an incident ray, pero nag-penetrate siya sa tubig, sa second medium, no? So you have medium number one nga hangin, medium number two nga tubig, no? Since the wave gets into the water, then the wave will change speed, no? As it changes speed, its tendency is to, no, change direction. Malain ang yung direction sinakaran, no? It is true for gases, it's true for light, it's true for sound, no? Nga nagatiko na siya, no? So the bending of the wave here as it passes through two different mediums, no, and changes its speed is known as refraction of waves, no? Okay, so what if kung puros na sila hangin? Then nothing happens, no? The wave will just simply travel in a straight path, no? But kung may ara ganing alain, no, like air to glass, no? You'll notice nga if light passes through a glass, no, ang light karon nagalain ang direction niya, no? It will now undergo refraction, no? So refraction. Now there is an angle also formed in refraction. We call as the angle of incidence and the angle of refraction. Usually, ining angle of refraction is towards the normal line. I think now kung towards the normal line kung denser medium, no, kundo mas magdasig di siya sa next na medium, so matiko siya towards the normal line, no? Okay, so light, no, or no, for light, no, it will bend towards the normal line, no, if the medium below is more dense, no, mas lapitanay ang iya particle, no? Okay, so refraction is another principle that we see, no, in our waves, no? Okay, so interference, no, a while ago, no, so we see this, no, that when waves interact with one another, no, then we can see that some of them will get larger, and at some points, no, they will nullify or cancel out one another, no? So the effect of interference. No? Now, the study of sound, guys, is known as no, acoustics. No? And we add some acoustics in a room, no, sa mga sinihan. Ginabutangan na sila naton sang rough na wall, no, para nga ang sound hindi mag-reflect. No? So we prevent reflection of sound in walls. No? Mayara na siya nga mga curtains, may mga ginabutang kita nga do mga giha-giha, no, do screen nga do kahoy, no, so that sound is not able to reflect back or bounce back. No? Because if we are in a room kagang sound do nagaumpok-umpok, no, ti paano kita ka-enchende sina karon sa nagahambal sa tunga, no. So as much as possible, echo, no, is suppressed, no, or is dapat idulaon na nila, no, in an acoustically designed room, no. So the study of sound, no, is known as acoustics, no. Now the sound wave, mabatian lang siya naton kung may amo ni siya nga frequency, no. The frequency suggested is 20 hertz, no, to around 20,000 hertz, no. So if it has this range, then our sound, no, is able to be heard. No, we call this as the audible frequency. Meaning natin ginatawag na audible frequency. No? If it is beyond or below this value, we will not hear it. No? So 20,000 hertz can be also written as 20 kilohertz. No? Pwede naman na siya sulaton as 20 kilohertz. No? So again, no, the range of value of the sound frequency, no, so you can hear it. No? Now, some animals, no, in the animal kingdom are able to notice, no, some vibrations below that value because they have a sense to detect it. No? But our eardrum, no, is only designed to detect, no, that range of frequency. No? Okay, there's also this thing about sound intensity, you know, that should be observed, no. Kung may ara kitang ano ni na sound yung gina-produce, no, beyond or sometimes, no, too much intensity of sound, no, can also damage our ear, no? Or it can produce pain already. No? So there's a sound intensity that is tolerated by our ear, and sometimes, no, there are also things na sobra na sa atong dulungan. Now this intensity value is measured in power, no, over area. No? So the power of the wave, no, which is in watts, and the area surface, which is in meters square. No? So you have here your I value, no, called your sound intensity. Again, no, the amount of intensity, no, can also, no, affect, no, how we hear things. No? Now the velocity of sound, no, here is one thing, no, that we see from sound. No? Sound can travel, no, in this way. It can bend downward, no, once there's a cooler air. No? So the bending of the wave there is that it's because it's slowing down. No? So since it's slowing down, then it goes downward. No? So at night time when air is cooler, no, we hear, no, people talking even though, no, they are in a considerable distance, no? Because again, the tendency of the sound is to go to the ground. No? So you hear a lot, no, people talking at night, no, than on daytime. No? On daytime, the tendency of sound is to move faster, so they go upward. So less likely that we hear people, no, during daytime, no? Because again, no, the tendency of the sound is to go upward. No? Now that bending of the sound is also known as refraction of sound. No? Echo is the reflection of sound. No? So when there's a hard object here, the sound bounces back. And again, bouncing back is known as reflection. So reflection of sound is known as an echo. No? So here's a wall there. No? So we see or notice an echo there. No? Now here's again an illustration of why sound refract. Again, when there's a difference in the temperature of air. No? Cooler air usually is heavier, so they are near the ground. No? But warmer air during daytime is usually going upward. No? So that's why, since the air is rising during the daytime, that our voice, or our sound, is always going up. Tendency of the sound is to move upward. So here is again, during nighttime, the kind of sound that you hear. This is also true when mag-ulan gid tapos ulan. So the temperature there is cooler, then the tendency of sound is also to go downward. Okay, here is an illustration of reflection also, So maybe that's sound waves, It bounces back, But if the medium is able to be penetrated, then it can go through, But there's a change in the direction of the sound there, or the wave, because of the difference in the medium. So definitely refraction will occur when there are two different mediums. Now, another concept that we have here is resonance. So what is resonance? Resonance is when two objects have the same or almost the same frequency. Now, considering this tuning fork, a tuning fork is a device that produces a specific frequency. If you vibrate the tuning fork, you will hear a particular tune, a fixed tune. Now, if you bring two the same tuning forks, so tuning fork A and tuning fork B have the same, they produce the same sound, or the same frequency. Now, if you let tuning fork A vibrate, now if they have the same frequency, naturally, if they're close enough, you'll observe that tuning fork B will eventually vibrate, even though you did not touch this. Now, where did the influence come? It comes from A. A will influence B, and B will vibrate because A has been made to vibrate. Now, that will only happen when they will have the same or almost the same frequency. Amo din ginatawag natin nga resonance. Now, resonance occur kung may ara kita radio station, we want to listen to a radio station. What we do to a radio station so we can pick it up, we have to adjust the tuning frequency. We have to match the frequency of the radio station with the frequency of our radio at home. You have to tune in the radio. So once they match, you'll notice that you can get a reception already. So the same is true for TV. If you are still using a TV, you have to tune into that signal or to that frequency, to catch or to watch the specific thing that is being shown in that particular TV channel. Okay, so resonance. You have to match the frequencies of two objects to be able to observe it. Now, why is our window sill, ang aton bintana nagauyog-uyog kung may mga bayli, ang aton cabinet, ang aton dingding naga-vibrate na sila kung maghuni ang bass sa aton nga sa mga bass na balang speaker, sang baylihan, nga nagauyog siya. There are events sa mga plaza, sa mga kondiinda, and you happen to have your house nearby. Manotice nyo kung may particular sound na nagauyog ang balay nyo. Okay? Now, that's an example of resonance. It will only rattle if that part of your house matches with the frequency of the sound that is being produced. So when they match together, they will resonate. Now, what's bad about resonance? So this glass is resonating kay nagmatch ni guro ang iya nga frequency sa isa ka nagahuni nga music. Bad thing is that ang glass dapat way naga-vibrate amo sini kay mabuka ni sana. So there are good and bad things about resonance. Good if it is in communicating signals. Bad if it is a breakable object like this, because it will eventually break. I think you've seen some movies where a lady sings and then for some reason the glass nagkalabuka lang. Ano kaya na natabo dito? Again, maybe we can explain that by the idea of resonance. Okay, tuning forks, no? So this is our tuning fork. May ara na siya nga mga marked frequencies dere, na? So do, re, mi, fa, sol, la, ti, do, go, ro, no? May ara na siya specific frequency where you can produce those specific tune, no? Or sound, no? In this tuning fork, no? So ining tuning fork, very useful device ni siya, no? Sa mga tao, ng mga musicians, no? Or mga tao nga naga-tune, no? Sang isa ka piano, no? Piano nga libagon, no? Ano na ninyo mabalaan kung anong sakto nga tunog yan, gamitan na nila tuning fork, no? And somebody will tighten the string there until they get, no, the right and correct tune, no? Now, Doppler effect, what is Doppler effect? Now, and this is the last one that we will cover, no, today. The Doppler effect is the apparent change in the frequency of a sound that is probably moving towards you or moving away from you, no? Kung may ara, da ambulansya nga nagapalapit, no, nga naga-travel, nga nagapakadto sa imo, you'll notice kang iyang siren, no, ang iyang huni, seemingly, no, hindi parehas, no? Okay? Nga hindi siya parehas. Again, no, because nga nagahulag ang nagaproduce sang sound or ikaw nga nagapamati, nagahulag ka, no? But try to imagine kung magpundo ang tao, no? Kasi ang tao nga nagapamati or ang salakyan nga nagahuni, kung magpundo na sa, then you will not observe anything lain. Now, you will only observe something different there when you are either moving or the car that you are listening to is moving, no? Now, we call that as Doppler effect. And what is Doppler effect? For example, in train, no? You'll notice that as this one goes towards you, you'll hear its frequency or ang yahoni nga medyo nagagahod, no? Or nagataas ang pitch, no? Okay? Di ba ang mga old nga mga train nga ini, no? They are producing some kind of nagabas di sila sang sound, no? But as it passes you by, paglabaya, no? Ang iya nga huni, nagnubo na, no? So again, no? Talking about the difference of the sound. But if this train is not actually moving, kung nagpundo ni siya somewhere di sa tunga, you will not notice any difference, no? You will not notice any difference in the way it produces sound, no? But maobserbaran mo lang na ang kinalain niya kung nagahulag siya, no? So the higher pitch is when it goes towards you, lower pitch when it is moving away from you, no? The same is true kung ikaw ang nagapapalapit sa iya, no? Let's say nagapundo ni sa, ikaw naman niya ang nagahulag, no? As you go nearer and nearer and nearer to the train that is stationary, no? Mabatian mo na ang yahuni nga medyo nagatingil ang iyang alarm, no? Or ang iyang sound, no? Okay, so that is true with this ambulance, no? As a moving ambulance will have a sound that is much higher in pitch than when it passes you by already, no? So that difference, that apparent difference in the sound is known as Doppler effect. Apparent na kay nga actually ang iyan nga huni hindi na lain-lain, no? Naglain lang na siya kay palapit siya sa imo or naga-move away siya sa imo, no? Okay, so here are characteristics of our Doppler effect, no? And that's our discussion for our wave.